This video will be about integration by part, solving some practice problem for integration by part. The first one, we need to evaluate the integration from 1 to 4 x ln x dx. As we discussed in the last video, that's one of the cases that we use integration by part and we use ln x to be u. So u is equal to ln x and dv will be x dx. The derivative of u du will be the derivative of ln x 1 over x, and the integration of dv, which is x, will be x squared over 2. Using the rule of integration by part, our integration will equal to u times v, x squared over 2 ln x, minus integration v du, and the constant have outside, so we have x squared over x dx. Simplifying x squared cancelled x, so we have only the integration of x, and of course we have a limit from 1 to 4. Substituting in the first term by the limit, it will be 16 over 2 ln 4 minus 1 over 2 ln 1 minus half the integration of x, which is x squared over 2 with the limits from 1 to 4. Of course, ln 1 equal to 0. So the first term will be 8 ln 4. And in this term, we have 1 over 4 times 16 minus 1. So the answer, final answer will be 8 ln 4 minus 15 over 4. We use integration by part in this example by selecting u as a ln x, and if we have a definite integral, don't forget that we substitute by the limit in the first term of the integration by part uv, and also in the second term, which is the integration of v du. The second problem in this video, we need to integrate the function sine root x dx from pi squared over 4 to pi squared. Of course, we can't use the direct antiderivative for integrating of sine, because the derivative of the argument of sine root x is not outside. But before we use integration by part, my advice, don't have a certain composite function, like we have root x as an argument of sine. So we must first, before using integration by part, we select root x to be 2t and use substitution from x to t. So we have now sine t, and of course we must calculate the differential dx, and also we must calculate the limits for t. So at x equal pi squared, root pi squared will be pi, so t will be pi, and at x equal pi squared over 4, t will be pi over 2. So we use our relation we select for substitution to get the limits for t, and also if root x equal t, then x equal to t squared, so dx will be 2t dt. So now we can replace dx by 2t dt. We can have the constant 2 outside the integration, and then now we have an integration in t, which is 2 times t sine t dt. It's clear that it is case number 1 in integration by part, in which we have a polynomial, which is t, times a function that can be integrated, which is sine t. So we selected t to be u, we have u equal t, and now dv will be sine t dt. the differential du will be 1 dt, and the integration of sine t, it will be negative cosine t. Now using the rule of integration by part, we have our integration equal to 2 times u times v, which is negative t cosine t, with the limits from pi to pi over 2, minus integration v du, and we have negative times a negative, so it will be positive, the integration of cosine t dt, with the limits from pi over 2 to pi. Substituting with the limits in the first term, we have cosine pi, which is negative 1, so this term will be pi minus cosine pi over 2, which is 0. And again integrating cosine t, which is sine t, with the limits from pi to pi over 2. Now our integration will equal to 2 times pi, and substituting the limit sine pi, it will be 0, and sine pi over 2, it will be 1. So finally, our answer for integration will be 2 times pi minus 1. Problem number 3 in our video today, it will be evaluate the integration e power root x dx from 1 to 4. Again, we need also substitution before evaluating the integration. So let root x equal t. So our integration will be integration e power t. We need also to evaluate the differential dx and to convert the limits 1 to 4 to t. At x equal to 1, t will equal 1, and at x equal to 4, root 4, t will equal 2. So our limit will be from 1 to 2 for t, and to evaluate dx from this transformation equation, we have x equal t squared, so dx will be 2t dt. So we can replace dx by 2t dt. Let's have 2 outside the integration, and now we have the integration from 1 to 2 t e power t dt. Again, it is case number 1 in integration by part, which is a polynomial times the functions that can be integrated. So we select the polynomial t to be u. So we have u equal t, and the dv will be e power t dt. And of course, we can use the Tipler method if you want to evaluate the integration directly. So du will be 1 dt, and the v will be e power t. Now our integration is equal to, using rule of integration by part, 2 outside, we have u times v, which is t e power t, minus integration v du, which is e power t dt, and we have the limits t from 1 to 2 in both terms. Now, substituting with the limit and integrate this term, we have 2 e power 2 minus e power 1, and the integration of e power t, it's e power t, and with the limits it will be e power 2 minus e power 1, and after simplification our integration will be 2 e power 2 minus e power 2, it will be e power 2, and this term e power 1 is cancelled this term, so it will be 2e squared. Problem number 4 in our video today, it's the integration of cosine ln x dx. Again, we can't use the antiderivative directly for integrating the cosine because the angle inside the cosine, which is ln x, we need its derivative outside. So since there is no 1 over x outside, we can't use the antiderivative. But before we think about integration by part, we have first to use a substitution. Let ln x equal to t. So our integration will be integration of cosine t. And of course we have to transform the differential dx to dt. So from the substituting equation, when ln x equal t, that means x equal e power t. So dx will be e power t dt. So we can use dx as e power t dt. Now we have the case number 3 for integration by part, in which we have the function cosine times the function exponential at its integration that can be rotated again to its value, to its form, after applying integration by part twice. So first we select u as cosine t and the dv as e power t dt. Du will be the derivative of cosine, which is negative sine t dt, and the v will be the integration of e power t, which is e power t. Now our value of the integration I will be u times v, which is e power t cosine t, minus integration v du, and the negative times the negative outside, so it will be positive, e power t sine t dt. Now applying by part again, the second time, let's say that u is equal to sine t and the dv is e power t dt. Again du will be the derivative of sine, which is cosine t, and v will be the integration of the exponential. Now our integration will equal the first term, e power t cosine t, plus applying by part for this integration, u times v e power t sine t, minus integration v du, which is e power t cosine t dt. This integration is the same form of our integration, e power t times cosine t, which is the value is assumed to be I. So we can write I instead of this integration, and collecting I in the same side, so we have 2I equal to e power t cosine t plus e power t sine t. Now I is equal to half times this term, of course the plus constant. Please don't remember that in some problems of integration you need a certain substitution before you think about the technique you use. Ln x equal to t is our substitution here to simplify the problem of integration to be just cosine t or cosine y. But after the substitution we have e power t outside. That's make the integration is the product of cosine t and the e power t times the e power t, which is case number 3 for integration by part. Our next problem, problem number 5, evaluate the integration of ln x power 2 dx. Of course now it's a direct case in which we have the integration of ln, and the integration by part will be powerful if we select u as ln x power 2 and the dv as 1 dx. The differential of u du will be 2 ln x times 1 over x dx. The derivative of ln x power 2 using the power rule, it's a 2 ln x times the derivative of inside the bracket, which is 1 over x, and the integration of 1 will be x. Now using the rule of integration by part, it will be x times ln x power 2, which is u times v, minus integration v du, which is x cancel the x, it will be 2 outside ln x dx. Now applying the integration of by part once, the power of ln x is reduced to 1, but still the integration of ln x need applying by part again. So let's we select u as ln x and the dv 1 dx. So the differential du will be 1 over x dx, and the integration of dv will be x. The first term in the integration, x ln x power 2 minus 2 times applying by part x ln x minus integration of v du, will x be cancelled the x, so it will be 1 dx. Now the integration of 1 will be x, so we have x ln x minus x plus c. In this problem, we apply by part twice. We apply integration by part twice because we have ln x to the power 2, and if we differentiate, select this term as u and differentiate it, the power will reduce to 1, and that's happened in the first time of integration by part. After differentiating another time, the power of ln x is 0, which is 1, so we can evaluate the integration of 1. Our next problem, problem number 6, if we need to evaluate the integration of tan inverse root x dx. Again, it's case number 2, in which we have ln or inverse function. In this case, we select the tan inverse to pu, but before we start integration by part, my advice is we simplify the function tan inverse by making the argument root x equal to t. So our integration will be integration of tan inverse t. And please don't forget that we need to evaluate the differential dx. So from our equation, x equal to t squared. So dx will be 2t dt. So dx is replaced by 2t dt. Now again, we can use integration by part. We can get 2 outside and use integration by part by letting tan inverse equal to u, and the dv will be t dt. The differential of u du will be the derivative of tan inverse, which is 1 over 1 plus t squared dt, and the integration of dv will be t squared over 2. Now our integration I is equal to u times v, and don't forget that we have 2 outside. U times v, it will half t squared tan inverse t minus integration v du, and we have the constant half outside, so it will be t squared over 1 plus t squared dt. Now we have an integration with the same power t squared and t squared. We can adding 1 and minus 1 and dividing this fraction into 2 fractions. So we have 2 half t squared tan inverse t minus half integration of 1 plus t squared over 1 plus t squared, which is 1, minus 1 over t squared dt. Now our integration will be half t squared tan inverse t minus half the integration of 1t, and 1 over t squared is tan inverse t plus constant. Problem number 7 in our video, it will be evaluating the integration of x power 5 e power negative 3x squared dx. we can use integration by part in this problem directly because we have a polynomial that's function. But before we start integration by part, my advice is to let negative 3x squared to pt to simplify the function e power. In this case, we have negative 6x dx is equal to dt. We need now to convert the integration from x to t. Be careful that we have e power t, negative 3x squared is t, and x dx, it will be negative t over negative 6, and we can write x power 5 at x power 4 times x, and the x dx, it will be dt over negative 6, dt over negative 6. Still we have x power 4, and from this relation x power 2 t over negative 3, so x power 4 will be t squared over 9. Now we can have 9 times 6 as a constant outside the integration. So we have outside 1 over negative 54, and we have e square e power t square e power t dt inside the integration. It is again case number 1 for integration by part, in which we have a polynomial time a function that can be integrated. We can use a Tipler method or the traditional method of integration by part. Let's say t square is e power is a function to be differentiated, and e power t is a function to be integrated. After differentiating 3 times, t square will be 0, and integrating e power t 3 times, and we can write the answer of the integration, t square times e power t minus and then plus again. So our integration will be equal to t square e power t minus 2t e power t plus 2 e power t plus constant. That is the final answer of the integration. The last problem in our video today will be problem number 8. Evaluate the integration ln x over x squared dx. It is again the case number 2 in by part, integration by part, in which we select ln x to pu, and dv will be 1 over x squared dx. The differential du will be the derivative of ln x, which is 1 over x, and the integration of dv, 1 over x squared, it's x power negative 2. So the integration is a power rule, x power negative 1 over negative 1, so it's negative 1 over x. Now using the rule of integration by part, our integration will be u times v, negative 1 over x times ln x, minus integration v du, which is negative outside, so it will be positive 1 over x squared dx. Again, the integration of 1 over x squared, which is x power negative 2, the integration will be x power negative 1 over negative 1 plus c. So the final answer is negative 1 over x ln x minus 1 over x plus c. Thank you.